Oh, all of you are at home, is it? So nice. Hey, where are the rest? Camera, please. I actually would like to I would like to take a snapshot of all of you. Forty-five of you. Muhammad Hamizan. Okay, I thought you are wearing a mask. Okay, all right. Darren. Okay. Who else? Zaidato, Awati. Oh, Shahidato, Munira, and Awati. You have the same background. Got confused a bit. Who else? Who else? There are some of you are still in and out of the classroom. One Muhammad Waiz, I saw you just now. All right, okay, thanks. Oh, relaxing, are you? Okay. Few minutes, please, everyone. Okay, just few minutes, huh? All right. For those who just joined, right, could you switch on your camera for a few minutes? I'll just wait for another 1 minute. All right. Make sure you have. Okay then. I'll start taking a snapshot right now. All of you, maybe you want to put on your best smiley face. All right. Okay. 1, 2, 3. All right. One more time. All right. Okay. Okay. Another time. 1, 2, 3. Okay. Well, how about one more time is freestyle? Okay. Any freestyle? Okay. One more time. 1, 2, 3. Oh, just a second. Somebody is joining. Okay. 1, 2, 3. Okay. Done. Okay. Let's start the class. You may switch off your camera if you would like. All right. Okay. Because it's taking a lot of data. Okay, let's continue with our lesson, last week's lesson. Zaidato is so happy, Zaidato, all right. Right. Now you should be able to see one of the activity that we actually I asked you to try to attempt it during your class session, the 1 hour class session. Now we have this activity 2.16. Just now I just share the notes of chapter 2 completed with the solution of all the activities basically. But of course, I've in your slides, right? I've actually renumbered the activities. I'm sharing the slide before I renumbered but anyway the question remained the same, all right? Which comes with the solution and then let's look at this activity. We have this trapezoidal channel. The lining of the channel is rough brick line. Rough brick. and then is carrying discharge. Now this discharge, look at its unit. Its unit is meter cube of second, so it's the uppercase Q, 25 meter cube of a second, which is the discharge lah, right? Longitudinal slope, which is the channel slope, channel's bottom slope, 0.004. Now analyze the proportion of, that means you are going to determine the dimension, alright? The dimension of a an efficient trapezoidal channel section having side of slope 1.5, horizontal, which would be, since vertical is 1, that means this 1.5 would be your Z, alright? And then the first part A, it gives you side slope, alright? But second part, B, it just, generally asks you to find the dimension for the most efficient channel section without the side slope. Now, for most efficient channel, you know that, from our previous analysis, we are able to show that the best side slope would be 1 over square root 3. That will be your Z, 1 over square root 3. So you can substitute, you can use all those formula given in the table. Now in part A, alright, which formula you are going to use is the one which has a longer formula, right? Which we have not attempted to get P minimum for a particular Z, alright, where we analyze for dP dZ lah, alright. So we have that formula. We are using the one that in your slide, which I put in the right box. All right. So now, rough brick line line channel, right? If you look at the Manning roughness coefficient table, you are going to get the Manning roughness to be 0.017. Right. Normally, all right, we'll just give you the description. What you have to do is you have to search for the Manning coefficient. Of course, we are going to provide you with the table, all right? So you don't have to search up and down, basically, right? Now, let's look at the first part. The side slope is fixed, so 1.51. So for bus hydraulic section, we know that A, equals to, you have y squared in bracket, 2 square root 1 plus z squared minus z, okay? This would be your best flow area. And then we also know that the hydraulic radius r equals to y over 2, okay? Of course, you substitute, since you know z is already 1.5, you substitute. Alright, so you are going to get A, the expression of A in terms of y, because we have solved for z, so it's 2.106 y squared. Okay, to 4 significant number lah. This would be 5 significant number already. So you can write 2.106, alright, y squared. Then of course, as I told you, the hydraulic radius will be half of y. You can show that, r equals to y over 2, no matter what side slope is given for trapezoidal channel, whether it is 1.5 or 1 over square root 3 or whatever side slope. And you can show that, the hydraulic radius is still the same, which is y over 2. Now, for Manning, since Manning roughness coefficient is provided, okay, or, based on, you read it from table, all right, based on the description of the channel's lining. So we are going to use the Manning roughness flow equation. Now, we are going, the purpose here is you want to get the dimension. Basically, what would be the best dimension for the best, most hydraulically efficient channel. Okay, so what you have to find is you need to find the depth of flow so that you can determine the depth of channel itself. Once you know the depth of flow, then you can estimate the depth of channel. Of course, it's going to be larger than your depth of flow, but you need to find the depth of flow. Trapezoidal, you know that you need to have side slope. Now, side slope is given already, which is 1 to 1.5, and then you also need to determine the bottom's width, all right? Channel's bottom width. That would be it. All right, you have the basic dimension already of channel. So now to do that, okay, your Q is provided, many you have found it, you know, the slope you have already also given in the question. So the only unknown here, that means y, you can solve for y using Manning equation. So therefore, you know, substitute r equals to y over 2, and then a, you know, your your flow area equals to 2.106 y squared. So solving it, you can find your y. That means the depth of flow in an efficient cross section will be 2.830 meter. All right. Therefore, all right, once you have y, you have z already. The final dimension you want to determine will be the bottom's width, b. Okay, so you know, using this equation, the only equation that you know, you have a, you have y, you have z, you can solve for b already lah. All right. Of course, here if you look at here, all right, I want to solve for b. My a I know is 2.106 y squared. All right. I also can, you know, substitute, because I already found my y. I can substitute for and solve for a. All right. You know, this is the second. This expression here is just, you know, rearrangement of a equals to by plus zy squared. How come the internet is not very good? Okay, you know, I just rearrange, making b as a subject of the equation. So I have those, substitute depth of flow. You should be able to find that your width channels, bottom width will be 1.714 meter. All right. Now this is let's solve it. All right. Okay. Oh, sorry. Thank you. I think just now, you know, there's a disconnection of internet. So thank you for pointing out. Okay. Okay, thank you, Mazatul. All right, let's continue. So therefore, okay, you should be able to find b equals to 1.714 meter. All right. That's it. All right. We're using your y, your b, and your z. You should be able to draw out the dimension already. Okay. So that is the basic dimension lah. You want to show that, you know, this would be the having such flow area or such Q, right, discharge, this would be the best dimension section that gives minimum P weather parameter and maximum Q. All right. But of course, the Q is constant lah in our case. All right. So this will be your minimum P. All right. You can try many other, you know, having the same constant area, you know, with the same Q, you can try many dimensions, but you will find that this dimension will give you the most, I would say, the minimum P, the minimum weather parameter. Alright. So far clear. I hope you know, this will be our last topic for chapter 2. I hope it's clear for you. Now, yeah, yes.
Kalau dapat 1.715, boleh ke?
1.715.
Right.
Yes, correct. Okay. Because you probably use A equals to 2.106, right? Yeah. Okay. Okay. Thank you. If you know, if you miss by, you know, to 2 decimal point or things like that, it doesn't matter, right? I'll just you get full marks as well. No worry. Now, second part B. All right. For part B, the side slope is not given. So you know that we have that go through the analysis. The most efficient side slope is 1 over square root 3. So substitute, you know, use this, and then, you know, your formula, remember the table of the best hydraulic sections, right? For trapezoidal, you just extract all those formula, a equals to square root 3y squared, because you know that when you substitute z equals to 1 over square root 3 in this formula here, all right, you would be able to get, you know, square root 3 over square root 3y squared. Okay, now solving it, and then okay, as r remain the same in the table, it's also provided hydraulic radius equal to half of y. Now in many equation you substitute, all right, a, you can actually, oh yeah, because y you don't know, you need to find y lah basically, so substitute the known values, all right, you know, so find for y, that means you can rewrite this in terms of section factor lah. That means you put ar to the power of 2/3 as a subject of the equation, then you can find your y, all right. So solving it, you'll get y equals to 3.045. There, all right. Hope it's simple, All right. Okay. You have found z as 0.5774. No unit, Z. You have found your y. All right. The third dimension that you need to find would be the bottom's width. All right. Which is equal to 2 over square root 3y. Where did you get it from? From that table. Okay. If you don't believe me, right, you can substitute, you know, your z and also your y. Sorry, your z and also your a in this equation here, all right, you are going to get, you know, your b equals to 2 over square root 3y. Okay, when z is equal to 1 over square root 3, okay, then substitute y. You already found that your y is 3.045, right, meter. Therefore, your bottom's width, channel's bottom width would be 3.516 meter, all right. So this is the, you know, having side slope 1 to 1 over square root 3, which is 0.5774. Right. So that's of it, All right. Now, this activity 2.17 is actually similar. I'm not going to repeat my, you know, explanation. It's similar to the previous activity. However, I just wanted to show, you know, the channels lining here uses gravelly earth trapezoidal channel. I just need to go to the Manning table, see if I have it here. Okay, here. So it's gravelly earth. Okay, you have gravelly earth. If you look at here, gravelly earth, right? It's actually is between the third one, earth, straight and uniform gravel. So between 0.022 to 0.03. I think I've explained this before. All right. You have a minimum range, you have a maximum range. All right. So which Manning n should you use? Well, to make life easier, you can use the average. That means 0.022 plus 0.03. You know, add them up together, divided by 2. So you get an average n. Or, you know, if you get to see the side itself, you say, oh, it's not that clean, you can increase your n to 0.03. Or, if it's really clean, you can use a smaller n. Now, to make life easier in analysis and we cannot go to the side and things like that, we can just take the average. But if you ask me, is it wrong to take 0.022? Or is it wrong to take 0.03? No, it's not wrong. You still get full marks, so it doesn't matter. But my advice is, well, actually for me, to mark your, you know, solution easily, you can just take average, right? But I don't mind, you want to use 0.022, is that correct, or 0.03, all right? Okay. So this is the average lah. I'll get 0.026. So you can repeat the same procedure as before for solving A and B lah, basically, All right. So I have the solution here. You can check it out. Try it yourself, all right? Before you check out, and I already shared this solution earlier just now, a few minutes ago. All right, same thing here. All right, I just give you more, exercises for you to practice on. All right, you have the solution, so it's easier. Now, this one is previous quiz, but okay. I plan to have one quiz with you too. Here is the thing. I want to ask you, are you interested to do revision this Thursday for test 1?
Boleh,
Sure, Doctor.
Alright, okay. So I'm going to share some exercises for chapter 1 and 2 for your Thursday. Because actually I also don't know what type of question, but I'm giving you some exercises. Then you can try it. We'll discuss the exercises on Thursday as well as Monday, because that Monday night, next Monday lah basically, that night you are going to have your test 1. So we'll look at it, alright? Do some revision this Thursday. Alright, but it's just for 1 hour as well lah, alright? Now, exercise 9, okay? We'll come back to this. I think you have learned this before, right? In previous activity, solution is there. Because I want to go straight to this topic here. We have a compound section. We actually have looked at, a couple of compound sections, channel section. Now, in reality, if you look at that diagram, right, in reality, the channels is not as nice as, this, for example, it's not as nice as this, all right, or even this, it's not, all right. It is always, irregular in shape, and between section also, it has different width, basically it's non-uniform lah, right? Okay, it's non-prismatic. Okay, the right word is non-prismatic in reality. However, in analysis, we tend to use a simplified section. So, even between section or even between sides, the same section, but between, both sides and bottom, it has different roughness. Channels roughness, be it Chazzy or Manning lah, it doesn't matter lah. Alright, it has different. So in case, right, you need to find, velocity depending on, various roughness. You could use this formula here, where V equals to K. What is K? Do you still remember what is K? It's convenience factor, right? It's Q over S naught to the power of half. And it's, of course, is equal to 1 over N and such on, right? Okay. Now, you can use this formula here, okay, to compensate. That means you have different K, which actually depends on your Manning roughness coefficient. So you can solve for velocity lah. Alright. I don't have exercises here lah, basically, because this is just for your knowledge. I probably actually in Benty Chow's book that I shared, the book actually consists of quite a number of exercises if you want to try on. Alright, we have this another activities, another activity that shows the cross section of river, and then you were asked to find what is the discharge. Okay, this is a compound section. You can divide it into 3, 4 subsection. It doesn't matter. It doesn't matter which, how many you divide it. It will come to the same answer. All right, using the formula that we have learned before. As I told you, for compound section, there are a couple of methods. Some reference book or even internet resources that you have found. Some reference book that or paper that you have found online, they will give you a slightly different method. The method that I show, that means, you find total A divided by your total P to get your R, hydraulic radius. That is one, it's a quite simple method. Alright, one way to find for your hydraulic radius for compound section, basically. So in our syllabus, we will just use that first, because whatever section that you are going to divide, you are going to get the same hydraulic radius. It doesn't matter how many sections, subsections you are going to divide, all right? Now, I have solved this lah, basically. You may take a look at it. It said we have already solved this kind of exercises previously, all right? This is just refresher course basically, for your refresher exercise, all right, for your additional exercises, all right, to improve your understanding. This as well. Okay, now in this case, right, if you look at the Manning roughness coefficient, right, you have various Manning roughness. So remember just now the formula that we are going to use, right? Okay, where does those formula, if you look at here, okay, if you look at here for varying n, okay, just a second, what I'm going to do, I'm going to enlarge the slide. Okay, if you look at here, for varying n, okay, the simplest way to do this would be, is, I could find for section 1, 2, and 3. They have different Manning, so I could solve for 1, 2, and 3 lah, basically, Q1 plus Q2 and plus Q3. So what I have to do is solve for Q1 first. Q1, of course, remember, the vector parameter is just, y plus b. That's it, or b plus y, it doesn't matter. Of course, a is still b times y, Okay, so you have that. All right, okay, you can solve for q, right? You just substitute 1 over n ar to the power of 2/3. I'll just go back a bit. Undo, go back, and then. Okay, then you solve for subsection 2, and then you have subsection 3 as well. Solving it, okay, you can add them up together, and then you are going to get, your total Q to be total Q, is it? It's in terms of Y, because Y is not provided here. Okay, you need to find YN. Okay, I didn't read the question properly. Okay, now determine normal depth for a discharge of 1600 meter cube per second. So you are going to solve for Y. So that means your discharge Q is all written in terms of Y. You have YN here. Okay, now you can actually solve for the trapezoidal section at the bottom here, because it's 5 meter, and of course your YN is more than 5 meter, right? So you could tentatively put a number or a symbol, for example Y1, to represent the remaining of YN minus 5 meter. All right, so if you look at this side, the diagram, I assume the remaining of Y0 minus 5 meter is Y1. So all my Q actually is expressed in terms of Y1, if you look at that. All right, if you look at the solution, is Y1. Therefore, I can actually solve for Y1. Now, my YN or Y0 is actually 5 plus Y1 lah. All right. So therefore, it's 6.286 meter. Right. Try it out. All right. Okay. This will be the last exercises. All right. I already provided the answer. Let me know if you have problem of solving all these activities, no matter from chapter 1 or 2. But of course, I would like, I would hope you, once you have finished a certain chapter, ask the question after the class, all right, or a week. Well, don't just wait until, a month or two to come back to chapter 1 or 2, all right? It's best if we just follow these chapters as we go, all right? So you need to prepare ahead lah. Okay, that is chapter 2. I'm going to give you one assignment for chapter 2. I forgot to upload it actually. I'm supposed to upload it earlier, but I'm giving you 1 week lah, all right? Time to complete assignment 2. I'm going to upload it after our class later. Alright, straight away because I already have it. Reason say I forgot to upload it in the author, so you may download the question, right? Try it on your own. This time, you know, your assignment for chapter 2 is, I think, only 2 questions, right? It's not so many, right? Now, just a second. Okay, now let's look at, we still have about 25 minutes. I'm going to go into chapter 3 a bit, okay? Chapter 3, all right, before I forgot. Okay, you have a slightly updated version basically. This is the previous version because I have, have all the solution in this slide here. All right. Chapter 3 is about specific energy and control section. Okay. We know that, right? In chapter 2, we have learned about uniform flow. Now, in chapter 3, we are going into non-uniform flow. But of course, for both chapter 2, 3, and 4, we are going to look at steady flow. Steady flow, but of course, you need to understand what this unsteady flow is about. Now, so chapter 2, we have looked at uniform flow. You see, in chapter 2, we determine depth of uniform flow, depth of flow in best section, we have Y naught, YE. Now, to determine depth of uniform flow, we are using Chasey and Manning Roughness flow equation. So in chapter 3, there's another new symbol that we are going to look at is depth of critical flow, which is YC. Alright, this is non-uniform flow. Let me ask somebody here. No, Shahidato? Can I ask you one question, Shahidato? Shahidato is not there. How about... No, Kamarina. Is Kamarina there? Kamarina? How come no one is... Awatif, are you there, Awatif?
Yes, Dr.
Okay. Awatif, I have one question. What is non-uniform flow? Oh, Zaidato. Okay, Zaidato, you have answered me, but it's okay. Awati, are you able to answer my question? What is non-uniform flow? Wait, how come I cannot listen? Oh,
Doktor. Aliran mana keadaan aliran yang berterusan tak tetap? Tak tetap, buka mic.
thank you. Okay. Remember that when we look at this slide here, unsteady, steady based on classification of time. Non-uniform and uniform is based on classification based on how it changes with space, right? So non-uniform flow ialah keadaan non-uniform berlaku ataupun tak seragam, aliran tak seragam berlaku apabila ukur dalam aliran berubah terhadap jarak. Maknanya pada lokasi A, ukur dalamnya contohnya 1 meter. Dia pergi bergerak 1 meter, ukur dalamnya berubah. Mungkin dia bertambah jadi 1.2 meter ataupun berkurang 0.9 meter. So basically maksud dia ialah aliran tak seragam berlaku bila ukur dalam aliran berubah terhadap jarak. That will be the explanation. Boleh tak Awati?
Boleh Doktor.
Okay. Alright, sama-sama. Okay, so non-uniform flow occurs when the depth of flow changes, alright, with space or in space, alright. That means at location 1, probably, the depth of flow is 1 meter, and then further down, right, it doesn't matter. Let's take an example. Further down, stream 1, apart 1 meter, location 2, the depth of flow becomes, increases to become 1.2 meter or decrease to become 0.9 meter. So therefore, the depth of flow is not the same between these 2 points. So that is non-uniform flow. That means the depth of flow changes right along the channel. Now, as I told you, right, there's a simple way to remember. The word steady, unsteady, there's a T there, right? So whether it changes with time or not, the depth of flow changes with time or not is actually is whether steady or unsteady flow. For uniform is whether the depth of flow. When I say depth of flow, of course, automatically it refers also to velocity of flow, because you know that when the depth of flow change, of course the velocity changes as well. As you know, this we are using mass of conservation concept where Q equals to AV, right? When the depth change, of course V velocity changes as well So I'm just using one parameter, which is the depth of flow. Okay, so uniform or non-uniform. For uniform flow, the depth of flow stay constant throughout the channel length, and then non-uniform it changes alright, along the channels. Okay, for non-uniform flow, right, we are going to look at gradually varied flow and rapidly varied flow in chapter 4. So chapter 3, we are going to look at depth of critical flow. Actually, we are going to look at specific energy equation, alright? I think this is what we are going to look at. We also are going to look at cases. What happened to the depth of flow when the flow goes over broad-crested wave, and when the flow through. If there's a channel, the width of a channel reduces or being constrict. So what happened to the depth of flow? Of course, it will change as well, right? So there will be various conditions depending on the width of the constriction as well as the height of the broad-crested wave. Alright, this is an interesting topic. So concept of specific and okay. So what is specific energy? Okay, specific energy is actually measured from the channel's bottom. Last time when we learned about Bernoulli's theorem, right, we would have 3 terms, which is the velocity term, we have the pressure term, and we also have the potential term, right, depending on the height. But in this case, since specific energy is measured from the channel's bottom, you are not going to use the Z term already here. That means the potential term which is measured from the term. So you have only 2 terms, which is the depth of flow and also the velocity, velocity head alright, which both of them are in meter unit. So E is meter as well. Specific energy is in meter. Alright. So now, this E equals to, let's see. If you are this E equals to y plus v squared over 2g, right? I could rewrite
Betul
this.
tak nampak?
Oh, sorry. Jangan mana? Okay. Okay. Kecil sangat ke?
Nampak boleh. Clear.
Okay, alright. If it's too small, okay, I'm going to stop presenting this. I'm going to present the whole screen. Okay, entire screen. But sorry, I'm actually purchasing a camera that does not autofocus. This autofocus is actually, I don't know how to make it non-autofocus. This is so much better. You have this specific energy E equals to y plus v squared over 2g. You can rewrite this because we know that, okay, Q is equal to AV. Alright, rewriting this by making V the subject of the equation, we have Q over A. So I could rewrite this equation here. I say E equals to Y plus, I know that my V squared is actually Q over A. When I said V squared, that means it's Q squared over A squared because I square both sides, right? So I have here Q squared over 2G A squared. So I could use any one of the equation depending on what data that I have to solve a certain equation. Now I have this. What if, alright? We have learned in chapter 2, we have learned about it is autofocus. Okay. In chapter 2, we have also learned about we are going to get headache because it keeps auto-focusing. Okay, now in chapter 2, we also learn about, for rectangular channel. This is only for rectangular channel. We also learned about, discharge per unit width. Remember this, right? Okay. Now, if I'm going to divide my Q, all right, that means, I'm going to have this expression. This is only apply for rectangular section. I can further this equation and this specific energy equation applies to all section, including rectangular. That means I can use this equation to solve for rectangular. I can use this equation to solve for triangular, trapezoidal, or circular section. Now, mainly for rectangular section, I can actually simplify this equation, okay? Because I know that I could use discharge per unit width, alright? So I can simplify this in case there is a question that doesn't give you discharge but give you discharge per unit width. So I can have this. Let's see. So if this discharge per unit width is given, I'm going to divide this by b squared over b squared. That means, okay, I'm going to divide this by b squared lah, and bottom as well, divided by b squared as well. But you know that this is 1 as well, right? So I'm going to have q divided by b, this is plus. Okay, this becomes q squared over 2gy squared. Okay, so this equation here only applies for rectangular section. Now, if the question give you for rectangular section, give you discharge, can you use this? Yes. If I have the width of a channel, I could actually simplify, right? By getting my discharge per unit width, and I could just straight away use my width. I don't have to find my A, right? That is to find specific energy. Okay, so I hope you are clear on this. All right, let's go back. I'm going to switch this. I didn't present the whole screen, but it's okay. All right. Allow. Okay, present now. A window. Chapter 3. Okay, let's go back. Okay, now let's go back to our slides. Okay, so if you look at this expression here, the specific energy, right? I could rewrite here to E equals to Y plus Q squared over 2GA squared. Okay, you have seen that, right? And then now what does it mean? This equation here, E equals to Y plus Q squared over 2GA squared. All right, I can actually plot out. Okay, this blue line, if you look at, okay, here's the thing. Let's go slowly, all right? For a channel, this diagram on your left, right, is the cross section of a channel. Imagine the depth of flow, all right? Changes from Y1 and then it reduces to YC. Let's assume it a depth of YC. Then it reduces to Y2. Okay, now if I plot, right, if I plot E to Y, all right, that means if Y changes, I can actually find my specific energy E, right? So, this is for a constant Q, the discharge remain, so I can actually find for E whenever Y, the depth of flow changes. So if I'm going to plot, all right, my E, right, I'm going to get the lines, the blue thick line, all right, on my graph. Okay, now let's I'm going to show you a just a second. I'm going to switch this back. Let's see. I'm going to show you the E-Y relationship on an Excel. Now, let's look at our Excel. Bear with me, we only have another 10 minutes to go. Alright. You should be able to look at the Excel file, right now?
Yes, Doctor.
Alright, Mazato, thank you. Now, let's imagine we have a rectangular channel. Alright, this applies actually to all sections. It doesn't matter rectangular or triangular or trapezoidal, but we'll just use a rectangular section, which is easier to compute. Right? Having the discharge, a constant discharge Q of 20 meter cube over second. The width of the rectangular channel is 2 meters. Alright? The width, it doesn't matter top width or bottom width, rectangular is the same. Alright? So the depth of flow, let's say, is 0.5 meter. So my A here, if you look at here, is B times Y. I'll get my A, which is the flow area. Okay. Now, I need A, Y, because I need to compute my E. E, the formula, if you look at this formula, is E equals to Y plus Q squared over 2G A squared. Now, if you look at my calculation here, I said Y is A6, right? Y plus Q squared, that means 20, this one. The red color, right? Red color, Q squared divided by 2 divided by 9.81, which is the G, divided by C6, purple color, right? Which is A squared. So I have my specific energy E here, all right, calculated, which gives me 20.8874. I have a 20. It's actually outside from this scale, because my scale, if you look at my X scale, is up to 10 only. Okay, but it's okay. There's a point that plotted. Then I said my depth increases another 0.5 meter. So my point is there, right? I have a point. Let's plot the point there. Okay. Format data point. Okay, not this one. Okay. Okay, then this first. Data series. Okay, I'm going to have built-in circle. Oh, too small, the rate. Okay, I'm going to option. Then I'm going to have the point there. If you look at it, right? I thought I picked circle, but it's okay. Now, that would be when depth is, if you look at here, the depth y on the y-axis is 1 meter. Okay, another thing. I don't mind you want to plot your y on the y-axis and your e on the, you want to switch it up, doesn't matter, but you have to understand, if you switch it up, the shape is a bit different lah, okay, basically. Now, there's this dashed line, e equals to y. What does it mean? E equals to y means, at this point here along the dashed line, right? Your e, when e is 2, your y is 2. When e is 4, your y is 4. That means e equals to y line, basically. It doesn't matter if your e is 3, your y will be 3 as well. So this dashed line e equals to y says that is the point where, your value e equals to y. Okay? So I draw a dashed line. You are going to see that your specific energy line would not cross that dashed line e equals to y. What does it mean? Okay, you see your equation, right? E equals to y plus q squared over 2ga squared, right? It says that your e, all right, is always greater than your y because you have y plus another term which is q squared over 2ga squared, right? So therefore, it would not, all right, cross your y. Dashed line, right? The e equals to y. So what if I increase it to another 0.5 meter, the depth of flow? So you have that, right? So let's see. Okay, I'm going to increase it further. I'm going to drag it. Oops. So if you look at that, if I increase it, this line is actually plotted from my E equals to, that means my specific energy equation. So you are going to have that line having the same Q, the same B, but you have changes in Y. Now, it comes to a point where you are going to get E, a minimum E, before it switch right. That means your E is going to, initially your E reduces, right, as your Y increases. Then when your y further increases, your e will reduce again. Okay, and your line of E, specific energy line, is actually going asymptote with your E equals to y line. Asymptote means it's not going to cross, but it's going near. Alright, now this E minimum, we term it as minimum E. Alright. And what correspondent, which y correspondent when E is minimum is actually YC, the critical depth. Alright, we could show actually critical flow occurs when E is minimum. We have those in slides. Alright, so I hope you understand, the expression there and the equation. Let's go back to our slide. And I hope you understand this EY curve. let me tell you this. It is important for you to be able to draw this EY curve. At least catch it, not really like draw it in high degree of accuracy, but sketch it, right? And you know how does this line comes, because when as Y changes, right, having the same Q, right, you are going to get one line, the blue line, right? Because as Y changes, E initially it will decrease, then it will increase. Now, what differentiate, you know, you have, as I told you, you have a point where E is the minimum, and the Y corresponding to the E minimum is the critical depth of flow. Now, when Y is less than your critical depth of flow, it is actually the depth of supercritical flow, YC. If you look at here, right, when flow is supercritical, all right, when Y increases, your specific energy reduces. For subcritical flow, when depth of flow increases, your specific energy increases. All right. So I hope you understand. The depth when Y is below, less than YC, it is actually the depth of flow of supercritical flow. When the depth, that means, you know, the depth along this blue line here, all right, is above critical depth of flow, it is actually the depth of subcritical flow. Now, for subcritical flow, we have learned in chapter 1 that when fluid number less than 1, it is subcritical flow, and when fluid number greater than 1, it is supercritical. Of course, critical condition occurs when fluid number is equal to 1, where velocity of flow is equal to the wave gravitational, the wave celerity, which is square root GD. Okay, we have shown that actually in first chapter. Now, you have alternate depths. Okay, now what is alternate depths? Let's go back. Oops, I keep switching. Now you see, let's say we have E mean. We also have E1 equals to E2. Now, for one E, apart from E mean, for other E, if you draw a line, straight line upwards, right? Okay, a vertical line, you are going to get two depths, you know. One depth to be, for example, in this case, E1 equals to E2, right? One depth is supercritical depth, the other one is subcritical depth. When I say subcritical depth, means the depth of flow of subcritical flow lah, alright? Okay, I hope you understand. Apart from E mean, for other E's, right, there are actually two depths of flow. Let me tell you this, if you are going to solve this equation, the specific energy equation, apart from when Y equals to YC, or apart from when E is equal to E mean, when E equals to E mean, there's only one Y solution. But when E equals to more, other E apart from E mean, you are going to get two different values of Y, because this is a non-linear equation. So you actually, when you solve it, you get two solution, for Y. So what are they? One is Y in supercritical condition, and the other is Y in subcritical condition. I hope you understand so far. Now, what depths is it? Having the same specific energy when you have Y1 and Y2, which is sub and super, right? Having the same E, these depths are called alternate depths. Okay. Now, in hydraulic jump, in case of hydraulic jump, when hydraulic jump occurs, hydraulic jump is a case of rapidly varied flow. When hydraulic jump occurs, there will be energy loss of energy, of flow basically. And then we are not going to call those depths as alternate depths, but instead we recognize it as conjugate sequence depths. I hope you understand when there's energy loss. All right, but in this case, we haven't touched about hydraulic jump yet. So we only know about alternate depths, but when we go to chapter 4, when we learn about hydraulic jump, therefore these depths are known as conjugate and secant depths. All right. So I've explained this. Again, I'm going to remind you, when you try solving for depth of flow, why? No matter, it doesn't matter why not, why E, why C, you won't get that negative depth of flow, If it's negative, that means, is it below the bottom of the channel? Then it couldn't be any depth, right? Okay, because we are not studying groundwater or whatever, right? Because we are studying open channel flow. So that means there's something wrong with your calculation, right? Negative depth is not possible, Okay, now you have this specific energy equation, right? We want to prove that when E is E minimum, or when critical depth occurs, fluid number is equal to 1. All right, let's prove it. Let's see. You differentiate E because you want to get E mean, right? So dE dy equals to 0 to get E mean. So differentiate your specific energy equation with respect of y. All right. So you have 1 minus. Okay. Now A consists of y. So you are going to do partial differentiation lah. Alright, so you have q squared. Q is constant. G is constant. Also, we have already mentioned it. So you have q squared over G. You differentiate A. You are going to have A cubic power. Alright, but you have negative 2. Therefore, you have negative 2. Divided by 2, you are going to cancel the 2, right? So differentiate again A, because you said A, we did A, you still have Y, all right? In this case, A is not constant, so you have dA over dy. So no matter what A expression is, you are going to differentiate again lah, dA over dy, all right? So at minimum specific energy, all right, we normally use Y as YC, all right? Critical flow. Later on, we are going to show that it is critical flow, and A is AC. So therefore, equating dE equal to dy, because we said E is minimum, right? We are going to show that Y is equal to YC. So equating it, this dA dy, right? We substitute it, become TC. How do you look at it? Now let's look at dA is an elemental of A. dy is an elemental of y. So you have dA dy here. If you have A divided by y, right, dA divided by y, you are going to get T, right? Let's say the top surface, because it doesn't matter what shape it is. If you take an element of it, you are going to get approximate of T, right, the width. So what you have here is Q squared over GA cubic power times T. Rearrange this equation, okay? Of course, one, you bring it to the, or this term, you bring it to the other side, you are going to get this, okay? Now, and then cubic power A, right? I split them up together because actually I want to have Q squared over A squared becomes V, because we know that velocity is Q is equal to A times V. So V is equal to Q divided by A. So therefore, I have V squared. And we also know that D is equal to A over T. So therefore, I have D here. So I have this simplified form after I simplified this term here. So square root both sides. Okay, I'm going to have V square root GD becomes 1. So it shows that when E is minimum, right, your fluid number becomes 1, or it is critical flow. All right. So Y is YC basically. All right. So this is another specific energy flow in rectangular section. The same thing. Okay. Since rectangular section, we are using this simplified rectangular section formula. I've shown you just now. So rewrite it. We want to show. Okay. Q is maximum. All right. When it's critical, so we are going to differentiate Q with respect of Y as well. Okay, this is the variation. I actually have the Excel of it, but I hope you understand that when Y changes, right, this is what your Q becomes. There is a switching point here. all right, where you get Q maximum lah, basically, and then it comes back, all right. All right, it's actually going upwards. Okay. Now, these are known as conjugate gaps. When you analyze hydraulic jump or hydraulic jump and things like that, you are going to use this specific energy, all right, in terms of Q and Y lah, all right. Now, remember, if we use discharge over unit width, this is actually normally for rectangular section, because you know that your trapezoidal section, you won't have, you have different top width and you have different bottom width, right? So it's not regular, right? So discharge over unit width, it only applies for rectangular section. Okay, now you differentiate dq over dy. So we are going to show that, still it is critical flow. All right. I'm going just another slide, right? Then we are done for the day. Now, state of flow can be established by comparing Y0 over YC. Actually, we have looked at this. We have compared when Y less than YC, it is supercritical flow. When Y greater than YC, it is subcritical flow. So you can summarize it. So when Y greater than YC, subcritical, Y less than YC is supercritical. Of course, you know that supercritical flow being fluid number greater than 1. Alright. So try out activity 3.1 yourself. You have the solution there, but try and calculate it. Who knows? Maybe there's some mistake in my calculations, right? You may check for me as well. Alright. And try all this. Okay, I think you can go. Okay. I'm not giving you the solution. I don't think so. I give you the solution there, but try it out. Then we'll continue. I guess, next Thursday then, because this Thursday we are doing the revision, right, for chapter 1 and chapter 2. Next Monday as well. So we are going to continue chapter 3 next Thursday then. Alright. I hope you are still okay. You are still with me so far. Do you have any question?
Setakat ni tak ada, doktor. Setakat ni lah. Doktor mute.
Please try, those simple activities, first few activities, try it out. Or I'm going to upload assignment 2 right now. Okay, after we are done with our class, I'm going to upload it and you can try it. All right. Okay. If there is no other question, I'll see you this Thursday for our revision class. All right.
All right, doctor.
Okay. See you guys.
Right, doctor. Thank you.
All
Thank you, doctor. Bye.
Thank you, Doctor.
Thank you, doctor.
Thank you.
Thank you, doctor.
You're welcome.
Thank you, doctor.
You're welcome. All right. Don't forget the attendance. All right.